Alright, so now that we've gone over a few different functions and how to take their derivatives, we're going to use those functions, or those derivatives, to make tangent lines that can approximate that function and be used to make calculations easier, at least in the real world, so that they don't have to do all the complex math, they can just approximate. So, first of all, how would you go about making a tangent line? What would be your first inclination? Let's say I gave you our function, good old function x squared, and I said make a tangent line that touches the function at the point 1, 1. So let me redraw that a little better. So here, that should be going to the origin, but here is the point 1, 1. So we have to make a tangent line that touches the function just right there. So it's something like that. And of course we can figure out what the slope is at that point using, if you want to do it the hard way, the limit definition of the slope, or just by looking at then saying that f of x is equal to x squared. Therefore, f prime of x is equal to 2x. So what is our slope at the point 1, 1? Well, f prime of 1 is equal to 2 times 1, which is equal to 2. So we know that the slope of that line is 2, and we know that it goes through the point, so goes through the point 1, 1. Well, how many ways can we make a line that goes to the point 1, 1 and has a slope of 2? The first way you might have learned it, and the way that I knew it when I first went into calculus, was with slope-intercept form, that y equals mx plus b, or ax plus b is probably how you learned it. But doing that, we know what the a is. The a is 2, but what's the b? Well, you'd have to kind of backtrack and say, well, if we're at 1, 1, and we go 1 to the left, since the slope is 2, we'd have to go down 2. So therefore, the b is negative 1. And we could have our function y equals 2x minus 1. And you can see that's roughly where it goes through. That minus 1 corresponds pretty well to that point. However, once you get to functions that aren't so close to the origin and don't have such nice slopes of good integers, it becomes a lot more difficult. So let's take another look at this problem and use a different formula called point-slope form. So once again, we've got our function y equals x squared. We know that the slope, which I'll call m, equals 2. And we know that we have the point 1, 1. Well, here is the definition of point-slope form, and you'll see that if you rearrange it a bit, you get back to your the slope-intercept form. So I'm just going to write it out right now and then explain what it means. So y minus y1 equals m times x minus x1. Now, the x and the y are just your variable. That's your variable. When you have y equals mx plus b, that's your same x and your same y. That y1 and that x1 correspond, so that is y1 and that is x1. It's your x and your y of your coordinate that you know. The m, of course, I even left the variable the same, is just your slope. So if we were to plug all of that in, we would have y minus 1 equals 2 times x minus 1. Now, that is technically the equation for the line. However, we can simplify it once again to put it into point-slope form, which is kind of the preferred means. So if we distribute that 2 through, we're going to get 2x minus 2, but then we're going to have to, if you distribute that 2 through, you're going to get 2x minus 2, but then when you add the 1 over, you're going to get y equals 2x minus 1. Surprising, or not surprisingly, that is the same formula that we got with the y-intercept form. However, we didn't have to do any calculations to figure out what the y-intercept was. We just plugged in things that we already knew. Now let's look at one more example. So let's say you wanted to find the tangent line that would approximate, or that you could use to approximate the function cosine, or cosine at pi over 4. So here's our cosine function. Does that. Here is pi. Here is pi over 2. And here is pi over 4. So how can we figure out that tangent line at pi over 4? Well, let's figure out our point and our slope. So the point's the easiest part. You don't need any calculus to do that. So what is cosine of pi over 4? Well, cosine of pi over 4, if I remember correctly, is root 2 over 2. Now, what about the derivative of cosine? Well, the derivative of cosine is negative sine. So what is negative sine of pi over 4? Well, sine of pi over 4 is also root 2 over 2, but now we have to make it negative. So it's negative root 2 over 2. And you should review your unit circle if that wasn't obvious. So now we've got our point, our slope, and we can plug it into our point-intercept form. So y minus our our y-coordinate is that root 2 over 2. So that came from that. Equals m, which is the slope, which is negative root 2 over 2, and that is that, times x minus, and our x-coordinate is the coordinate that they gave us, pi over 4. So that is the tangent line that would go through the function cosine and be just barely touch once at the point pi over 4 and root 2 over 2. So now let's talk about the utility of tangent lines. What's the point? Well, let's say that you were running a computer program and your computer program didn't want to have to calculate all of cosine. It only really needed values that were kind of in this narrow window right around the point pi over 4. Well, rather than calculating cosine at those values, which can take a lot more power than simply using this linear function right here that we could simplify, but I'm not going to do just because it would take time. You could use that linear function, and if you zoom in, if you were to zoom in on that point in the cosine function, so you see, zoom in a lot, there's the cosine function. Actually, if you zoomed in enough, it'd just barely be curved. And then here would be our linear approximation. Now you can see that for all those points around pi over 4, so here's pi over 4, for all those points around, they're pretty much the exact same, especially if I had to zoom in more and more. The value is practically equivalent, so you can use far less computational power and use that linear approximation. So tangent lines make linear approximations. Approximations save computing power. Now, one other quick point is called the normal line. So go back to our example with cosine, and so let's sketch the cosine function. And we wanted the linear, the tangent line approximation at pi over 4, which looks something like that, and it was touching. Now, something else you can use is called the normal line. Now, the normal line goes through the exact same point, however, it's perpendicular to the tangent line. So that is the normal line. So how do you find the normal line? Well, how do you find a line that is perpendicular to another line? The slope of the normal line is equal to, so m of the normal line is equal to negative 1 over the m of the tangent line. So that m corresponds to that line, that m corresponds to the normal line. So in our last example, I think the slope was still root 2 over 2, or negative root 2 over 2. So in this example, the m would be, the slope of the normal line would be 2 over root 2. So I flipped them, and I made it the other sign. So that's a normal line. You might use it in your class, so I just wanted to show it real quick here. So that's tangent lines, approximations, and normal lines. See you guys next time.